So right now, what we're going to do is we're going to do several rotation volume integrals. Before we actually do the different versions of this problem that we're going to do, I have first written down the region that we're going to be rotating about different axes, just to get an idea of how this works. So we're going to find the volume of the figure bounded by y equals e to the negative x squared. Let me write that down here. Y equals e to the negative, I'm sorry, not negative x squared, I'm sorry, negative x over 2. I apologize about that. Okay. And also x equals 0 and x equals 3 and y equals 0. Okay. So I'm going to draw that figure here. This is my y-axis, obviously, right? The vertical axis. This is my x-axis, the horizontal axis, as you know. Now here, I'm saying that it's going to be x between x equals 0 and x equals 3. We know this, the y-axis is synonymous with x equals 0. And we know that x equals 3 is somewhere over here. So we'll just call it like this. Now, of course, when we write x equals 3, we mean the vertical line. But for us, we basically know that it's going to be like a little fence here that's going to somehow bound our region. Okay. Now, if you know your parent function of e to the x, you know that e to the x can be written, or e to the x looks like this. E to the x goes like this. It has as its horizontal asymptote the x-axis. And let me see here. Okay. And it will get closer and closer to x as you let x get small, as you let x get small, right? And of course, as you go to the right, it'll go up to infinity, right? Now, if we replace x by negative x, we know that that's a reflection about the y-axis, right? Because if you take the negative of x, every one of these values, like let's say x equals -1, will go in here and become e to the positive 1. Let's forget about the 2 for a moment, right? So that shows you that it's reflecting across the y-axis. So that means that instead of this graph looking like this, it's going to look like this. Okay. Okay. And of course, as we go up to infinity, the e to the negative x over 2, this curve is going to get closer and closer to the x-axis forever. Never touching, but getting closer. Now, of course, at x equals 0, we know that negative 0 over 2 is just 0. So e to the 0 is 1. So we actually know that it crosses here at y equals 1. Okay? And here, we know the y value that it crosses there, maybe not as an explicit decimal number, although we can get an approximation using a calculator. But so we know that this is going to be the point 3 comma e to the negative 3 over 2. And we know that this is the point, as we just highlighted, 0, 1. And so the region bounded by y equals 0, which is the x-axis, x equals 0, which is the y-axis, x equals 3, and this curve is this region that we can shade in here. Okay. Now I'm just going to copy this into the corner so we can save our important points. And then we're going to start looking at several different integrals that we can set up to find the volume depending on what axis we would want to rotate it about. So now I want to set up the integral for volume about the x-axis. But I want to remind you about the formula that we're going to use and what is the rationale behind this formula. Okay. So right now I'm just going to draw an f of x just for the sake of our discussion, not related to the problem, but just so that I can show you the idea about what's happening here. Let's say that this is my f of x, and I want to rotate it about the x-axis. Then, and let's pretend that this is the x value A, and this boundary is the x value B. And in other words, you can see that if you were to rotate it like this, we would be getting the volume of something that looks like a kind of like barrel. Okay, okay, okay. So what's going to end up happening here is that if I imagine I slice it here at a particular value of x, which we'll just call x star to give it a particular name, obviously without compromising our generality, and we think about this vertical distance here, then we know that that vertical distance is this function value evaluated at that value of x star, right? Just like if I want to plot, like let's say y equals x squared, right? I can start plugging in values. Like if I take x equals 1, then I know 1 squared is 1. If I take x equals 2, then I know that 2 squared is 4. So I know the y value is up here. And then if I plot enough points, then I get this beautiful parabola. Obviously, this is not a beautiful parabola because I just did it real quick. But if you plot enough points and take your time, it'll be pretty. But so in other words, what I wanted to emphasize here is that this distance is the function value evaluated at a particular x value. So in other words, even though here like the symbols might make it look more complicated, I want you to realize that we're not talking about anything we haven't seen before. So now what I want you to imagine is this. If I actually rotate this, okay, I'm going to get a kind of circle. I'm going to get a circle if I rotate it, right? And then here, if I imagine I give it a small thickness, oh my God, this is the worst drawing I've ever done. And let's say this has width delta x. So in other words, if I take a small thickness here and I make a circle and I make this circle and I make it a cylinder by making it that thick, then I can actually calculate the volume of that cylinder. The volume of a cylinder in general is pi r squared h, right? Which you know we know from elementary geometry, pi r squared h. In this case, our pi stays as is. Our radius is the f of x star. So we're going to be putting f of x squared. And of course, we can put the x star here. And then the h, in this case, this cylinder, as you can tell, is kind of lopsided. It's on its side. It's tilted. So, but we can see that that height will be delta x in our picture. So now if we add up all the contributions of the area from slicing it like this into slices, where let's say this is x1, this is x2, this is x3, this is x4, this is x5, and so on, then what you end up with is lots of little cylinders, right? And let's say like this. And a little cylinder here, right? And of course, you get the picture. So this term, right, is just the area of one of these cylinders, right? And if I add them all up and I let the thickness, delta x, go to 0, I can relabel it as a dx just for the sake of discussion. Then I get our integral formula for our volume of a revolution. So volume by revolution is going to be v. It's going to be the integral, in this case, from the a to the b of pi times the f of x squared dx, right? I want to highlight the most important, kind of like skipped a couple of steps here, but the most important things I want you to realize is this, what that f of x is. I can tell, I know that you guys are with me on the geometry now, but the f of x here is the radius of the thing you're rotating, okay? Okay, and the pi f of x squared comes from the pi r squared. The dx is basically a representative or an, let's say, a vestige of this delta x, the idea that we're slicing it into many slices. Okay. So now let's apply this formula to this problem. The problem at hand, and remember, right now our goal is just to set up these integrals. We're not going to actually calculate them, although we could definitely do so if we wanted to. But for right now, I just wanted to look at this figure and set up the integral. So this is 3 This is 0. This is our f of x in this case. F of x equals to e to the negative x over 2. We know that this crosses at 0, 1. And of course, we know the point here is at 3 comma e to the negative 3 over 2. If we want to rotate this one about the x-axis, as I've done here, what I want you to realize is that the radius of the object that's going to be rotated is just the f of x value. Okay. And so you can see that the volume, the object whose volume we're finding kind of looks like a kind of like a street cone that's been cut or that's laying on its side with its base removed. Okay. But of course, given this situation and given that the function is the radius and we don't have to think about that anymore in that sense, because the function is the radius in this case, then we know that the integral will just be in this case from 0 to 3, pi. Our f of x is just e to the negative x over 2 squared dx. That would be the integral that would represent the volume of rotating this region about the x-axis. Okay? And remember, we got a huge simplification here from the fact that the f of x here is just the radius of the object of the function being rotated. So we didn't have to modify it at all. So now I want to figure out what the volume would be of the figure that would occur if we were to rotate our region about the y-axis. Okay. So one of the things I recommend you to do is obviously you graph your figure originally like we did in your paper, but then for each individual different kind of like rotation or modification of the problem that you're going to do, you can make small little drawings that capture the important portions of the problem. Okay. Okay. And of course, remember, this was the region that we stipulated in the beginning of the problem. It's the region bounded on top by the function f of x equals to e to the negative x over 2, on the bottom by y equals 0, i.e. the x-axis, x equals 0, i.e. the y-axis, and x equals 3, this horizontal piece here. And now in this part, we want to calculate what happens, what would be the volume if we rotate it about the y-axis, right? Like this. Okay. So what I want you to notice is, if you look at it in a moment, I want you to look at it carefully. And I want you to notice that it kind of splits naturally at this height. Because what I want you to realize is that from this y value, which we already know is, oh, whoops. From this value, y value, e to the negative 3 over 2 down, this radius is the same. So in other words, we have here like a small cylinder, okay? But then from here all the way to here, it's the x coordinate, right, of the value, right? So basically, if you look at this curve, or in other words, it's bounded by this curve. We're gonna see how to get that in a moment. So f of x, again, remember, is equal to e to the. So in other words, the corresponding x for a particular y value, because as we go up, the y is changing, and we're gonna need to know what that x is, because that'll end up being our radius if we're rotating it like this. Okay? Okay, finally said that properly. That's fantastic. Okay. So in a case like this, where the radius will be constant for some interval, in this case from interval from 0 to e to the negative 3 over 2, we can just use the volume of a cylinder formula to find the volume of this piece. And then we can use an integral for this piece. If, on the other hand, just for the sake of discussion, that this had been a different function in this region, like let's say something like this, then we would have had to do two integrals, one integral for this part here and one integral for this part here, okay? But we know that in this case, in this part, it's just vertical there. Okay, so let's partition that here. And again, remember, we're just going to set this integral up. We're not going to actually evaluate it explicitly because right now we just want to see how to do this. And of course, up here, the upper limit of the y is 1. And the reason why, again, the reason why we're going to integrate with respect to y is because our slices are going to be like this. So the radius is going to be the x value for a given y value, okay? Okay. So let's call the bottom figure that'll occur from this revolution as the bottom. We'll call it B, and we'll call this upper figure the top. Okay, no surprise there. Okay, so the volume of the bottom, which we'll call VB, is just going to be the volume of a cylinder, pi r squared h. In this case, the r is going to be the 3, right? So pi times 3 squared times the height, which will be e to the negative 3 over 2. So we're going to now do the part where we need to do the calculus and where we need to do the setup of the integral, okay? That is this part here. So as I've mentioned before, and as you've heard me say it before in this problem, we need to find the x distance from the y-axis to the curve for a given value of y, so that we can set up the integral in terms of y. Okay, so let's do this here. So if y is equal to e to the negative x over 2, I want to solve it for x. Now we know that the ln of e to the x is equal to x because that's one of the inverse properties of the log. So what I'm going to do here, knowing this fact, is I'm going to take the ln of both sides. The ln of y is going to equal to the ln of e to the negative x over 2, like this. Now, because of what we just said, we know that the ln of y is going to equal x over 2, right? So now we're going to multiply both sides by negative 2, and we get that x is equal to negative 2 ln of y, okay? So we're going to, for this problem, we're going to delete this temporarily, and we're going to write that this curve can be represented as x, which we can see as now a function of y, is equal to negative 2 ln of y. Okay, perfect. So just as we did with the slicing along the x, which was like this, we knew that our formula was b equals the integral from a to b of pi of f of x squared dx. Here it's going to be the same, except everything will be written in terms of y. And in this case, the slicing is going to be in terms of y, right? Like perpendicular to the y-axis. Okay, so now we can set this up. This is going to be the integral from the bottom, which is going to be e to the negative 3 over 2, to the top, which is 1, which is here at that apex, and then pi. Then our f of y in this case, negative 2 ln of y, and then squared dx. This would be the integral that represents the volume of this top portion, okay? And so the volume of the whole figure would then end up being the volume of the top portion plus the volume of the bottom portion, okay? Let me see here. And of course, we're not going to evaluate those integrals, but I wanted you to see how we would set them up so you could see the logic behind them. And let me see here. And also let me point out the reason why we didn't have to finagle at all with this value, like this x value, for example, is because you can see that for any y value, this expression gives us exactly this distance. So in other words, it exactly gives us the radius of the region at any point. Okay. And for example, if you're like paranoid like me and you want to just sanity check it, you could ask yourself, if y equals 1, does this in fact give me a radius of 0? Well, the ln of 1 is 0. 0 times negative 2 is 100 million. I'm just kidding. 0 times negative 2 is 0. So we can see that indeed the radius there would be 0. And if we take this value here, right, just as again, as a sanity check, you don't have to do this. We could ask, what is the f of e to the negative 3 over 2? Again, we're using f in terms of this f of y here. So that would be negative 2 times the ln of e to the negative 3 halves. And again, because of the inverse properties of the log, i.e. that the ln of e to the x equals x, we know that this is going to be negative 2 times, times negative 3 over 2. When you multiply those out, the negative times the negative will be positive, the 2's will cancel, and we'll be left with 3, which is exactly the x value, the radius at that height. So this function does in fact exactly correspond to the radius of the figure that's being rotated for those given y values. And again, if we want to find the volume of this region rotated about the y-axis, what I wanted you to realize in this case, because the region split into two pieces, one bounded by the curve and one bounded by this vertical line, we had to split that volume calculation into two pieces. One of which we were fortunately able to just use the cylinder formula because the radius here would be constant, and one which we had to calculate by setting up an integral, and which we then had to solve for the x, which was the radius in terms of y, so that we could do the integral along the y-axis. Okay, now let's get another example. So now we're gonna do a slight modification. What if we want to find the volume of the figure that would result if we were to rotate it about the line y equals 7? Okay, let's think about what that is. Let's try and visualize this here. And here I'll draw this big, okay. Oh my God, this pen is kind of giving out on me. Let's see. So let's say this is 7 here. This is 1. This is 3. All right, this is the region. And we're going to rotate it around this line. Right, this is our axis of rotation. So in other words, what I want you to imagine is that this will end up looking like, I guess, what would look like if you take a bottle cap, like from a 7-Up or something, and you remove the top. It'll look like something like this. And it'll have like this cross section like this. Kind of like the inside of a rocket cone or something like that, but not as pronounced, obviously. But kind of like this, right? This inside is all hollow, right? But we want to find out the volume of this material, right? And you might say, well, David, why would we care about the volume of such a material? Maybe we work for a company that does blow forming of plastics. That's when you take plastic pellets and you melt them and you use them to form a shape in a mold. Like for example, a lot of the plastic goods we buy are made in this way, blow forming. It's very economical. And so calculating the volume of a figure like this would let us know how many pellets to buy, right? Okay. So now the way we're going to do it is like this. What I want you to notice is in this case, we're going to actually have two situations. If we're going to rotate it like about this line, we're going to have this outer region, which you can see is equidistant from the line of rotation, right? Imagine that if we just close this off for a moment, right? What I want you to realize is from this line of rotation, the y equals 7, to the x-axis, that has the same distance the whole way around. And aha, look, it's just this inside that needs to be removed, right? So here's what we're going to do. If you notice what I'm seeing, then I can calculate the volume of the outside as a cylinder. In this case, again, we're lucky that this x-axis is exactly the same distance the whole way as the axis of rotation. So I'm going to call this the volume of the outer. And again, in this case, we're fortunate because of the reason I mentioned that we can calculate that as a cylinder. So pi r squared h. The r in this case will be the 7. So this will be 49. And the height will be the 3. So 3 times 49 is 147, I believe. And then times 5. So 147. Let's do that real quick here with a pencil and paper so we don't make a mistake. 49 times 3, 27, 4, 8, 12, 13, 14. Yeah. Okay, we're right. Okay. So this is the volume of the outer. Now here's where it gets interesting. I want to find the volume of the inner. In this case, what I'm going to do is I'm going to calculate this distance here. Okay? Because if I can find out the volume of this figure, the hollow, then I just subtract it from the cylinder and I get this piece here. Now remember, this function is f of x equals e to the negative x over 2. And as we've mentioned before, we know that from this axis of rotation, y equals 7, to the base, it's 7. And that's true from x equals 0 to x equals 3, which are the x boundaries of the region of interest to us. So what I want to claim to you here is that this radius of rotation of the inside part of this function, of the inside part of this object is 7, this distance, minus this distance, which we know is given by that. So the volume of the hollow, so I'll write it here as a hollow so we don't forget it. This is not what we want to calculate, but we are calculating it to make our life easier, and we're going to subtract this hollow from the outer. So the volume of the hollow will be from A to B, so in other words from 0 to 3, pi, the radius of the object that's being rotated, which of course, as we just showed visually here, is this thing, which is 7 minus e to the negative x over 2 squared dx. I want you to notice that this is the radius of the hollow. See, as I go from x equals 0 all the way to x equals 3, no matter for any x value, if I take 7 minus the f value there, e to the negative x over 2, I get this distance that is the radius of the hollow. So using this formula, I get the volume of the hollow. So the volume of interest to us, the volume we care about, the volume of the object, I'll just put OBJ to represent object, is going to be the volume of the outer, 147 pi, and we're going to go from 0 to 3 pi, 7 minus e to the negative x over 2, close parentheses squared, dx. So that's going to be this is the volume of this kind of annular type of shape that we talked about earlier, right? And I want you to really pay attention to the way I drew this figure so you can see how it's done. So now let's see what would happen if we wanted to rotate it around the line y equals negative 2. Let's draw that in here real quick. Negative 2 is down here, as you know, and our region is like this. We know that we want to rotate this region, right? And we're going to rotate it, oops, sorry about that, around this line. Let's think about that. What I want you to realize is that we're going to have a hollow on the inside, but what I want you to notice is that in this case, the x-axis is uniformly distant from our uniformly distant from our axis of rotation. So in other words, the inside is going to be a cylinder, right? We know that this is 3, this is 0. So let's calculate that. So the volume of the inside, i.e. the hollow, actually, let me just point that out, by the way. You look at this figure and you imagine rotating it. What I want you to realize is that on the outside, it's going to look something like this, okay? And if we were to cut it, we would see that it would have a cross section on the inside. This part here is hollow, and it's a cylinder. So what we're going to do is we're going to first calculate the area of this cylinder, the volume of this cylinder, which we can see has a radius of 2 and a height of 3 because it's on its side. And then we're going to calculate the volume of the outer as if it did not have the hollow cut out of it. And then we're going to do the subtraction. So as we mentioned, the volume of the hollow is going to be a cylinder. So pi r squared h, which is going to be pi times the radius, which we saw is 2, squared, times h, which is 3. So in this case, 2 squared is 4. 4 times 3 is 12. So 12 pi. Okay. Now we're going to do the volume of the outside. Okay. So the outside radius is this. Okay. And if we go from 0 all the way to 3, what I want you to realize is that it's always going to be 2 plus the function value, right? So in other words, this radius, let's call this r of x, is going to be the 2 plus the f of x. Like this. So the volume of the outside is going to be the integral from 0 to 3 pi times our radius, which is 2 plus e to the negative x over 2 squared dx. And so then the volume of this region rotated about the y equals negative 2 axis is going to be the volume of the outer, which would actually be this region without the hollow minus the volume of the hollow. So the volume of the figure is going to be the integral from 0 to 3 pi 2 plus squared dx minus 12 pi. Okay. So now we want to set up the integral to calculate the volume of the figure if we rotate it about the line x equals 5. I'm going to draw my figure. We know that the region goes from x equals 0 to x equals 3. And in this case, we want to rotate it about x equals 5. So it'll go about this axis like this. So what I want you to notice is that in this case, we're actually going to have two different situations. We're going to split it here. Okay. If you imagine rotating it, you're going to see that the other piece, right? And what I want you to notice is that this bottom part is basically going to be like a washer that's kind of thickened, kind of like a donut. But then this part is going to be, as you can see here, kind of like a bowl on the inside, but a cylinder on the outside. Okay. Okay. So we're going to call this part the bottom. We're going to call it B, and this part the top. And what I want you to notice is that for the bottom, it's going to be the difference between two different cylinders. The outer cylinder minus the inner cylinder. Okay? And in this case, we know from the previous part of the problem, from our first graph of it anyway, that this point is 3 comma e to the negative 3 over 2, that point there. And we know that this point is 0, 1. Because since we're going to do the rotation about the x equals 5 axis, which is this one, we know we're going to have to integrate along the y. But check this out. As I mentioned before, though, I want you to notice that at least for the bottom part, we don't need to do calculus because we just have the outer cylinder minus the inner cylinder, right? So the bottom, we'll just do that real quick. The volume of the bottom is going to be, notice how from the axis of rotation to the outer, from 0 to 5, the radius is 5. So it's going to be pi times r squared h, so r outer squared h minus pi r inner squared h. As we just mentioned, the r outer is 5, and the height is e to the negative 3 halves. And then minus pi, the r inner, from 3 to 5. 5 minus 3 is 2, so that inner radius is 2 squared, times the height is also e to the negative 3 halves. So you can see here, I can factor out a pi, I can factor out an e to the negative 3 halves, and I get 5 squared, which is 25, minus 2 squared, which is 4, which is 21. So I get 21 e to the negative 3 halves pi as the volume of the bottom, right? Now we're going to worry about the top. Okay, here we're going to have to be very careful. Okay. Now, remember, this curve is y equals e to the negative x over 2. So if we solve that for x, and I'll remind you why we're doing that in a moment, we take the ln of both sides, and remember, this is true because we know that the ln of e to the x is equal to x. So if I take the ln of y, I get the ln of y. If I take the ln of e to the negative x over 2, I get negative x over 2, right? Because of the inverse property of the log. Then here I multiply both sides by negative 2, and we can see that x is going to be negative 2 times the ln of y. Now here we have to be very careful. What I want you to notice is this. So let me rewrite this part here using this notation. And then we're going to draw the picture a little bit bigger so you can be 100% with me on what's happening here. Right, we know that the x, this distance, is negative 2 ln of y for whatever y value is in here. Okay, so let's look at this together. So this is my drawing of this part that's above this horizontal line. What I want you to notice is this. This is 5 here. And what I want you to realize is this. If I look at horizontally, okay, this distance from here to here, from here, the axis of rotation, to x equals 0, i.e. the y-axis, we can see that that's 5 uniformly. This curve, for any value of y that we have here, this distance is going to be negative 2 ln of x, right? I'm sorry, negative 2 ln of y. So in other words, that distance is that for a particular value of y. So in order to find out the volume of this piece that we want when we rotate it around the 5, what we're going to do is we're going to find out this radius here. We're going to call this the Rn, okay, the inner radius. And what I want you to know, so the Rn, because if I calculate the volume of that, that'll be the volume of the hollow, okay, on the top anyway. So here we're looking at only the top. The volume of the hollow is going to be the integral. In this case, we know the y value at the bottom is e to the negative 3 over 2, and it goes all the way to 1. The pi, and now the radius. We know that this distance from here to here is 5 because it's from 0 to 5. So 5 minus x which is the negative 2 ln of y. In other words, the 5 minus wherever we are in the curve here, this x value, will leave us with the radius from the axis of rotation at that y value. So it'll be 5 minus, and since that's a negative 2, so I'll just put it in here, 5 minus minus 2 ln of y, and then squared, and then dy. And now notice, I haven't mentioned it yet, but I want you to realize the outer is a cylinder also. It's a cylinder from with a radius of 5 and a height of 1 minus e to the negative 3 over 2. So the volume of the outer on the top part is going to be pi r squared h. The r is 5. The h is 1 minus e to the negative 3 over 2. So that's 25. We can distribute this, right? And so it'll be the outer minus the volume of the hollow, and then plus the volume of the bottom, the volume of the whole figure. So now we can see that the volume of the figure is going to be the volume of the bottom. So 21 e to the negative 3 over 2 pi plus the volume of the outer, which is pi times 25. So 25 pi times 1 minus e to the negative 3 over 2. And then minus the volume of the hollow for the top, which is this integral from e to the negative 3 over 2 to 1 times pi. Now this 5 minus minus becomes 5 plus 2 ln of y, and then squared dy. So this expression gives us the volume of this shaded figure if we wrap it, if we rotate it about the x equals 5 axis. I hope you've enjoyed these examples, and I hope you've enjoyed these examples and that they're helpful. Thank you.